Okay. So let's continue with the coupled climate variability, and we have mentioned already the alphabet soup of modes of climate variability with many different time scales. So this is the so-called North Atlantic Oscillation, or NAO, which is majorly the oscillation between the Icelandic low and the Azores high, and you can use your knowledge about the role of pressure gradients and Coriolis to see how the change in this pressure gradient changes the flow, let's say from North America over the Atlantic into Europe, and it can make obviously a massive difference. So you can see that in the NAO negative phase you have cold snowy conditions here with jet stream dipping and warm and less sea, whatever that means. Cold and dry here, warm and wet. I think I should be careful. Less sea ice. I'm sorry, I can hardly read what is written. So snowy and dry, warm and less sea ice. So the Labrador Sea gets warmer climate because you have warm subtropical air inundating into higher latitudes as opposed to cold dry air coming down all the way into lower latitudes here, and so on. So oftentimes you can see debates about where is the global warming when it's so cold here, but you have to make sure that you understand the pattern of how the jet stream is making warm and cold patterns, which is then leading to the debate about whether the jet stream is migrating more, wandering more meridionally because of sea ice loss and Arctic warming and polar amplification and so on. So let's leave it there, but you can see in the NAO positive mode this is stronger, so you have flow going this way. So you have warmer conditions here. These are basically anomalies. So you have cold and more sea ice here, warm and wet conditions here, cold and dry conditions here. Okay, so that's the NAO mode, and there are some evidences that this is related to the Arctic oscillation. So whether there is an annular mode in the northern hemisphere that is also related closely to the North Atlantic Oscillation is something that is still debated, and looks like there is a high correlation anyways. And something like NAO has lots of timescales in them. It can vary literally on few weeks timescales to interannual and decadal timescale, but what matters is when it gets stuck in one phase, more preferably over, let's say, many years. Okay, so there is a southern annular mode which involves the subtropical front, subantarctic front, the polar front, and southwesterly winds, and so on. So we have always talked about how the Southern Ocean is special because it's a channel and winds can churn the ocean, send the wind forcing and Ekman currents deeper to the bottom, and in fact bottom drag and bottom topography can become an important factor because the Ekman currents can go that deep, and that water can inundate the Indian, you have to be careful where you are. So this is the Pacific sector, Indian sector, and the Atlantic sector, and so on. And this southern annular mode has an impact on tropical climate as well, like the Indian Ocean, Indian monsoon. Okay, this is the Atlantic multi-decadal oscillation, where the North Atlantic remains warm or cold for multiple decades, and then some interhemispheric gradient is defined as an index. So each of the modes tend to have indices which are then used to track them, predict them, look for their predictability, look for their teleconnections, and so on. Okay, so Atlantic multi-decadal oscillation, here you can see the magnitude here is fairly tiny, but nonetheless you have a positive warm phase of AMO here. So you can see this remains above when you look at the 5-year average annual tropical cyclone count. So this argues that when the AMO, Atlantic Meridional Oscillation, is in its positive phase. You have warmer sea surface temperatures here, which you intuitively would expect to have an impact on cyclones. And when it is in the cold phase, the cyclone 5-year running mean cyclone count goes down. So a particular year may be high, but on average count remains low. Okay, so those effects are important as well. Let's now come to another topic that we have discussed already many times, not only in my other courses, my writings, but also in this course already in terms of Bjerknes feedback. We'll revisit this mode here because it continues to be the most dominant mode of climate variability at interannual timescales. And as we said, because the climatological or normal temperatures in the East Pacific are cold, and ocean is taking up heat when that's cold, it becomes critical to understand how the east-west sea surface temperature gradient and hence the pressure gradient, hence the winds and the feedback respond to global warming, right? If under global warming this warms less than this, that means the trend will be for an increased east-west temperature gradient, which would drive stronger winds, and continued cold or less warming trend here, which means ocean heat uptake will continue, and that would moderate the atmospheric warming signal, the global warming signal. Okay, so at the El Nino at interannual time scales is still associated with the waxing and waning of this upwelling, as we saw in the Bjerknes feedback. When it is a normal year, so this is the average for 2002 to 2017, so long-term average including El Niños, La Niñas, and so on. You can see that during an El Nino here in this is the normal time when you have cold upwelling conditions along the coast here, strong chlorophyll concentrations in milligrams per meter cube, and the upwelling is strong along the equator and extends all the way to the date line here. So you can see that the cold, nutrient poor, production poor waters are stuck to the subtropical gyres where you have convergence sinking, so nutrients are not at the surface even though light may be available. So these are the Hadley cell coming down, and ocean desert. So similar latitudes you have deserts on land, but in the ocean also you have deserts in terms of phytoplankton. And you can see that under the ITCZ the wind stress curl, elevated thermocline, and intermittent wind forcing can still drive phytoplankton productivity there. Okay, so this is during the El Nino event of 2015, which was the strongest in the 21st century so far, and rivaled the 97, 98, and 82, 83 El Ninos of the 20th century. So you can see the dramatic change here in the front between the equator and the nutrient and production poor region here, and the ITCZ here, and the reduced upwelling and reduced chlorophyll concentrations here as well. So there are many details that are involved. Each El Nino doesn't necessarily look the same, and it depends on at what time you look at the signal, because the strongest upwelling here happens in June, July, August. So if you look at the same time, upwelling obviously doesn't completely disappear because you still have trade winds, so upwelling is greatly reduced and its westward extent is greatly reduced. So you can see the blue waters with very low chlorophyll are much more extensive here as well as here, and there are some wave patterns which have to do with the change in the wind forcing and so on as well that we will not get into. So this is a biological indicator of the Bjerknes feedback that results in the SST gradient being weaker, upwelling being weaker, winds being weaker, nutrient supply and chlorophyll being reduced as well.